Word ladder. This is the graph problem interviewers love. Word ladder. It looks like a toy puzzle. Change one letter at a time, but secretly tests BFS instincts, hashing, and pre-processing. This Pattern Mastery 100 favorite appears at Meta/Amazon screens because many candidates brute force neighbors and time out. We'll blitz it with basic and finish in clean on_middle.l squared, or better with bidirectional BFS. We're given begin word, end word, and a word list. Each step you can change exactly one letter, and the new word must exist in the list. Return the length of the shortest transformation sequence from begin word to end word, counting both ends. If impossible, return 0. Shortest number of steps in an unweighted graph? That's BFS. But we can't build edges naively, too slow. Instead, pre-process using generic patterns. For each word, replace each position with two form keys like HT or IT. Words sharing a key are one edit apart. Then BFS from begin word using this pattern map. Complexity. Build map in on_middle.l keys and traverse neighbors in on_middle.l squared worst case. For extra speed, we can run bidirectional BFS from both ends. If end word not in the list, return 0. Put all words into a set. Ensure begin word is included for pattern generation. Build patterns. Dict str, list str, by replacing each position with standard BFS, Q holds, word, distance. For each popped word, iterate its patterns and neighbors, in queue unvisited neighbors at dist +1. Mark visited as soon as in queued. Let's wrap up the word ladder problem. Time complexity is OM times n times 26, in the worst case, where m is the length of each word, n is the number of words in the dictionary, and 26 represents trying all letters at each position. We start with DFS with backtracking. The begin word is our starting word, the end word is our target, and word list is the dictionary of valid words we can use. Think of this like exploring a maze of words. We start from the begin word and try changing one letter at a time. At each step, we check if the new word exists in the dictionary. We keep track of the shortest path to reach the end word. If we find a dead end, we backtrack and try different letter changes. In our Java solution, we begin by creating a blueprint called solution, where we write our word ladder solving recipe. We create a scorekeeper initialized to infinity, so any path we find will always be shorter. The main function takes 3 inputs, the starting word, the destination word, and a list of valid words. We convert the word list into a set, organizing it for faster searching. First, we check if the end word is even in the dictionary. If not, we return 0. Then the adventure begins as we call our helper function DFS, starting with the begin word and a step counter of 1. After the search completes, we check our scorekeeper. If it's still infinity, there was no path, so we return 0. Otherwise, we return the shortest path length discovered. The DFS function is our explorer. It tracks where we are, where we want to go, the dictionary of words, and the number of steps taken. If the current word matches the end word, we update our scorekeeper with the smaller of our current best or the new steps recorded, then stop exploring this path. We also skip any path that has already exceeded our current best length. We transform the current word into an array of characters, allowing us to change letters individually. We look at each position one at a time, remembering the original letter before trying all letters from A to Z. We skip the original letter and replace it temporarily with a new one to create a new word. If this new word exists in the dictionary, we remove it temporarily to avoid cycles and recursively explore deeper. Once done, we add the word back, allowing other paths to use it, and restore the original letter to continue. This depth-first search explores one path completely before trying alternatives. Backtracking ensures we don't get stuck in loops, and pruning prevents exploring longer paths than necessary. Be mindful that each recursive call uses stack memory, so very long word ladders could risk stack overflow. Now that we've implemented our BFS solution for the word ladder problem, it's time to test it with an actual input. This step shows how the algorithm behaves in practice and ensures that our logic produces the correct result. We will walk through the input, observe how the solution processes it, and confirm that the output matches what we expect. Let's test our function using this input. We have a starting word hit, a target word cog, and a dictionary of words that we can use to transform hit step by step into cog. Here's why the solution works. The algorithm uses a breadth-first search to explore all possible single-letter transformations from hit. It keeps track of visited words to avoid repetition. Step by step, it finds the shortest sequence of transformations leading to cog. For example, the chain hit hot.dog gives a total of 5 steps, which is the shortest path. And that is exactly what the program outputs, 5. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully finds the shortest transformation sequence between the start and end words. It handles the given input correctly and produces the expected output. BFS ensures efficiency, avoids unnecessary repetitions, and guarantees the minimal path. M. In practice, which is much faster than regular BFS. Here, N is the number of words and M is the length of each word. Using bidirectional BFS reduces the search space dramatically. We use an optimized solution called bidirectional BFS. Instead of searching from only the starting word, we search from both ends, from begin word and from end word. The two searches meet in the middle, which makes the path much shorter. Every step tries changing each letter to all possible letters, checking if the new word is valid. By exploring from both sides, we cut the search depth almost in half, making the algorithm significantly faster. Imagine it like two people searching for each other in a maze, much faster than one person wandering alone. In our Java solution, we start by importing all utility tools we need, sets, queues, and lists, like preparing your toolbox before building something. We define a solution class that neatly wraps our code. The main function receives the start word, the target word, and all the words we're allowed to use. We convert the list of words into a set so lookups become super fast. If the end word isn't in the dictionary, we immediately stop because transformation is impossible. We create a queue to explore words step by step, starting with the beginning word, and a set to remember which words we've already used so we don't repeat them. We mark the starting word as visited right away and initialize a level counter to track how many steps we take through the transformation. As long as the queue has words to explore, we continue our BFS search. For each level, we process all words in that batch before moving to the next. For each word, we take it from the queue and check. If it matches the target word, we return the number of steps it took to reach it. To explore transformations, we convert the word into a character array so we can easily modify each letter. We go through each position, saving the original character before trying every letter from A to Z. If the new letter is the same as the old one, we skip it. Otherwise, we replace the letter and form a new word. If this new word is valid and hasn't been visited, we mark it as visited and add it to the queue for exploration in the next level. After checking all possibilities for a position, we restore the original character. After finishing all words in the current level, we increase the level counter. If we finish everything without finding the target word, we return 0, meaning no transformation path exists. And that's how this algorithm works. It prepares the words set, queue, and visited map, then explores all one-letter transformations level by level using BFS. By expanding outward efficiently, it finds the shortest path. Efficient, simple, and elegant. Bidirectional BFS dramatically reduces search depth, tests every position with 26 possible letters, and ensures valid words are used only once with the visited set. In practice, this makes the solution very fast. Before checking the output, let's understand the problem. We are given begin word equals hit end word equals cog a word list equals hot.dog log. The goal is to find the shortest transformation sequence from begin word to end word, changing one letter at a time, using only words in the list. If no path exists, the function should return 0. Let's test our function with this input. Here, cog is not reachable from hit using the given words. Here's why the solution works. Bidirectional BFS. Start from both begin word and end word to expand towards each other. Always expand the smaller frontier to optimize search. Generate neighbors. For each word in the current frontier, try changing each letter from A to Z. Only add new words if they are in the word list and not visited. Check for meeting point. If a new word appears in the other frontier, a path is found, return the current length. If no path is found after exploring all possibilities, return 0. Step by step with this input. Hit hot, possible, hot dot or lot.dog log, but cog is missing in word list, so the frontiers never meet. The function correctly returns 0. And that is exactly what the program outputs, 0. This confirms that the code handles cases where no transformation path exists. So, our implementation is correct. It successfully identifies when a word ladder is impossible, efficient, accurate, and reliable. Our implementation is correct. It correctly identifies when no path exists. It efficiently searches using bidirectional BFS. It returns the correct shortest length when a path is possible, or 0 if impossible. Let's wrap up the word ladder problem. At first glance, it seems like a simple word game, changing one letter at a time, but underneath, it's a classic graph challenge that really tests your BFS intuition. Breakdown recap. We started with the idea of transforming a begin word into an end word, step by step, where every new word must exist in the list. Our goal was to find the shortest path from start to finish, and if it wasn't possible, we'd return 0. Assess recap. To solve it efficiently, we recognized that this was a shortest path problem in an unweighted graph, perfect for BFS. Instead of brute forcing every word connection, we optimized using pattern preprocessing, where we replaced each letter with a wildcard, creating keys like a, t or it to group words that differ by just one letter. Structure recap. From there, we structured our approach. First, check if the end word exists in the list. Then, build all pattern mappings and perform BFS to explore word connections layer by layer, counting each transformation step until we reach the target. Implement recap. After implementing it, we ran the code on LeetCode, no errors, smooth execution. Check recap. When we tested it with multiple cases, the outputs matched perfectly, confirming our logic worked as expected. The big takeaway? Word ladder isn't just about words, it's about recognizing graph patterns and using BFS smartly. Once you see that connection, the path to the solution becomes crystal clear.